Chapter 3, Molecules and Compounds. There are about 91 different elements that exist in nature naturally. There are more elements, there are 118 elements on the periodic table because everything past uranium, which is atomic number 92, has been synthesized. So 91-ish exist naturally, and then the rest are synthesized. But there are way more than 91 substances in the universe. And this is because it is these elements can combine to form different compounds. So just like how our 26 letters of the alphabet can combine to form, millions and millions of words, the 91 elements can combine to form millions, billions of compounds. Remember, we talked about this before. The atomic elements are the single atom elements. That's most things on the periodic table. It's kind of that beigey gray color are the atomic elements. The molecular elements are two or more of the same atom bonded, and they are highlighted on the periodic table. The ones you really need to pay attention to and memorize are those yellow ones, the diatomics. The phosphorus, the sulfur, the selenium, that's not really going to come up. We might talk about it again, but it's not really going to come up. Those diatomics, however, you absolutely need to know. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. The fun trick that I like to use is that now there's hydrogen, and hydrogen, as we've talked about before, is always just kind of off doing its own thing. So you just have to know hydrogen. But there are 7 diatomic elements. And look at this. They start at number 7, nitrogen, and they kind of make a number 7-ish, if you draw a 7 weird. So starts at 7, makes a 7. That's what I like to say to help you remember those diatomic elements. And then, of course, add hydrogen to that as well. When 2 or more elements combine to form a compound, an entirely new substance results with new chemical properties. And new physical properties oftentimes. These compounds are chemically combined, as we've talked about previously. So if you look at the properties of hydrogen and the properties of oxygen, and then the properties of water, you can see how different they are. Hydrogen and oxygen are both gases. They have very, very low boiling points. Hydrogen is explosive. And then we get to water, much higher boiling point. It's liquid. So they have very different properties than the elements compounds have very different properties than the elements that make them up. So a good example of this is sodium and chlorine. Sodium is a soft metal. In the last chapter, I showed you guys that video of sodium reacting with water. So we know that sodium does react violently with water. Chlorine is a yellow toxic gas. If you've taken world history and you talked about World War I and mustard gas, a component of that was chlorine. So if you inhale chlorine, it will kill you. So these are both very, very dangerous things as elements. And yet when they combine, they're a very common substance, sodium chloride. So remember the law of definite proportions, which states that any compound, no matter where it is produced or the size of the sample or whatever, will always have the same elements in the same proportion by mass. So for example, water is always 2 hydrogens to 1 oxygen. So compounds are composed of atoms held together by chemical bonds, and these chemical bonds result from attractions between the charged particles, so the electrons and the protons that compose atoms. Electrons are negative, protons are positive, so they are attracted to one another. Chemical bonds are broadly classified into 2 types, so ionic and covalent. In an ionic bond, an electron is lost, usually by the metal, and then that electron that was lost, as you saw in the video, is gained by the nonmetal. So ionic bonds are always metal, nonmetal. In covalent bonds, electrons are shared, and that's going to be 2 nonmetals only. So when a nonmetal bonds to another nonmetal, they share electrons because both nonmetals would want to gain electrons and they can't do that, so they share. So again, ionic bonds, metals tend to lose electrons, nonmetals tend to gain. When metals lose electrons, they become positively charged. When nonmetals gain, they become negatively charged. And then the ionic bond is the attraction between that negatively charged anion and the negatively charged nonmetal and the positively charged metal. And when things are bonded ionically, it's called an ionic compound. So the basic unit of an ionic compound is a formula unit. Ionic compounds they have a crystalline structure. So there's a very regular repeating pattern of the ions, but the formula unit is this, I guess I'll say, the simplest ratio of the ions. So in the sodium chloride crystal, there's many, many sodiums, many, many chlorines, but when you break it down, it's a 1-to-1 ratio. And that's why we say the formula of sodium chloride is NaCl, 1 sodium to 1 chlorine. So this is just kind of showing you the formation of that ionic compound. So that sodium is going to lose an electron and form a cation. The chlorine is going to gain that same electron. So the electron's transferring from the sodium to the chlorine. That forms an anion, and then the cation is attracted to the anion. And when a bunch of those get together, you form your crystal, and you get your sodium chloride. Covalent bonds occur between two or more nonmetals, and electrons are shared between them. So with ionic compounds, it's called a formula unit. With covalent bonds, it's called a molecule. What happens is that those electrons are attracted, or shared electrons are attracted by attracting the positive nucleus of each atom. That sentence is very unclear, I'm sorry. So the electrons basically of one atom are attracted to the nucleus of the other atom, and so that's what's going to hold those atoms in place. Covalently bonded compounds are also referred to as molecular compounds, so I will probably use those terms pretty interchangeably. Oops. I don't know how I made subtitles. I made it go away. So the basic unit of a molecular compound is the molecule. And unlike ionic compounds, molecules don't get together to form one giant structure the way that happens in ionic compounds. They just stay the individual molecules. Polyatomic ions are very, very, very important. You are going to need to memorize these. You will not, this is one of the very few things I have you memorize. You will not be provided a list of them on any of the naming quizzes or tests or anything in the future, so you do absolutely need to know them. Polyatomic ions are an ion composed of two or more atoms. So those atoms are covalently bonded that make up the ion, but then the overall thing has a charge. So an example of a polyatomic ion would be, let's say carbonate is one. So carbonate is CO3. And then that C and O, they're two nonmetals, so they're covalently bonded, they're sharing electrons. But then the entire thing has a -2 charge. And so it acts just as any monatomic ion would. It acts just like oxygen or sulfur when forming ionic compounds. These are your polyatomic ions that you will need to memorize. Memorize me. You'll need to know their formulas and their charge, of course, because it will absolutely come up when we are doing naming, which would be in the next section. I think that's it. Yep.